You build a secure enclosure, lock the heavy bolts into place, and assume the contents are safe. Then, the entire frame shatters outward. This is a standard pattern in Spring Boot. A developer wraps a target method in a transactional annotation and includes a try-catch block to handle expected errors. The code executes as written. The try block attempts the operation, an exception occurs, and the catch block handles it. But despite the successful catch, the database transaction irreversibly dies. The logs report an unexpected rollback exception. The framework indicates the transaction has silently rolled back, even though the Java code appeared to recover. This happens because the developer's mental model treats transactional as a simple code boundary. In reality, it is a complex coordination of physical resources. To resolve these failures, we have to unpack the underlying machinery: AOP proxies, thread local state maps, and the physical state of the database connection. Treating the framework as physical infrastructure is the only way to manage these hidden transaction failures. The Java code you write is not the code the JVM actually executes at runtime. Spring uses CGLib or JDK dynamic proxies to intercept your methods. These proxies wrap your classes and contain the logic that starts and stops transactions. When an external caller hits the proxy, it opens a database transaction before delegating the signal. But during self-invocation, method A calls method B internally. The signal loops, the proxy is skipped, transaction logic never triggers, and method B runs unprotected. Without crossing that external proxy boundary, the transaction does not exist, leaving your database operations vulnerable to partial failures. Once the signal passes the proxy, Spring must share a single database connection across decoupled classes, but it does so without passing a connection object as a parameter. It manages this through the Transaction Synchronization Manager. This manager uses a thread local map, binding a JDBC connection to the executing thread. Subsequent calls retrieve that exact connection. But @async spawns a separate thread from a pool. This new thread's map is completely empty, cutting off access to the parent transaction. Transaction boundaries are tied to thread boundaries. If you switch threads, you lose the rollback safety net of the parent transaction. This explains why logical Java methods and the physical database connection can fall out of sync. Spring's default propagation is required. This forces nested methods to join the active physical transaction instead of starting a new one. Left, Java code; right, shared physical pipeline. If method B throws an exception, Spring permanently sets a rollback-only flag on the pipeline. Method A catches the error in Java, but the physical flag remains. A's commit attempt hits this, triggering an unexpected rollback exception. Catching an exception in the Java code does not fix the state of a tainted physical database connection. To avoid this, developers often use requires new to force the inner method into its own isolated transaction. Requires new pulls a second connection. Under load, this drains the pool, causing deadlocks. Alternatively, Propagation.NESTED reuses the same connection by dropping a save point. If an error occurs, it rolls back just to that marker, preserving the outer transaction without wasting physical connections. Save points provide logical isolation without the resource costs of opening multiple physical connections. This reveals a unified model. Proxies handle the calls, thread locals coordinate execution, and propagation manages the physical connection inventory. We can use this understanding to improve performance with the read-only true flag. While many assume this flag blocks SQL writes at the database level, its primary benefit is actually internal to the application. When using Hibernate, this flag switches the session to flush mode.manual. The system bypasses the heavy snapshot and dirty checking processing node. By skipping the creation of memory-heavy entity snapshots and dirty checking loops, read-heavy operations see a measurable efficiency gain. @transactional is a tool for managing physical resources. Its behavior depends on the alignment of the proxy, the thread, and the connection. Predictable backend engineering comes from understanding the physical infrastructure